Okay, so it says evaluate that function. That's nice. So first is evaluate f1 of 1. So f11 is going to be
ln of 1 plus 1 minus 1.
ln of, yeah, 1 plus 1 minus 1, which is ln of, which is 0. Yep, nice. So then it asks you f of e1. That's nice. So it's ln of plus 1 minus 1, which is ln e, which is 1. Find and sketch the domain of f. So the domain, you know that x plus y minus 1 has to be greater than what? 0. So x plus y has to be, so y has to be greater than, oh, 1. Sorry, thank you. 1, negative x plus 1. So when you graph this, negative x plus 1, is it solid or dotted? Dotted, and it crosses at 1, right? And it's negative 1, so you have that as your boundary. And then you figure out, do you shade above or below? We'll plug in 0, 0. Is 0 greater than 1? No. So where do you shade? Above. Always test a point. Please test a point. Don't just take it on logic. Just test a point. Usually, what point can you always test? 0, 0. What? Well, people are like, oh, it's greater than, so it must be above. That's what I mean. It's not always true. Just be careful. Be really, really careful. This is the sketch. If you're going to sketch it, this is the sketch. What you could do before you sketch it is you could say the domain is, the proper way to say it would be all the points x, y such that either way, y is greater than negative x plus 1. That's fine.
You could also do x plus y.
Exactly. Any of these. Going right there is fine.
So it doesn't have to be a function.
No, absolutely not. No, of course not. I mean, we had x equals y squared before. Remember, like x is greater than y squared. It was the sideways parabola. Yeah, we're not grounded in functions anymore. A log function. What's the general shape of a log function? What's it look like? Kind of goes like this.
Yeah.
So something like this. Is that true? Right?
It's steeper than log.
And this is the what? It's the, is that the y-axis right there?
Yeah.
Yeah, because is it okay?
The axis
Where's the axis?
a little over the arrow.
Like this?
Yeah.
Is that what it looks like?
Yeah.
Yeah. Does that make sense? Yeah, can you plug in ln of 0? No, you can't evaluate. You can't plug in a negative number, but can the output be negative?
Yeah.
Sure, absolutely. When it gets, yeah, absolutely. So you want this thing to be big. So if we want this thing to be big, the output to be big, if we want the output to be big of this thing, we want the inside of what you're taking the logarithm of to be what? Huge. We want this to be as big as you can, right? How big can you make it? Really big, right?
Infinity.
So that's the up. So there is no upper bound. It goes to infinity, right? The real question is, what's the smallest?
Infinity.
How far down can you go?
Infinite.
Yeah, you can make it. No, well, no. Can you make it? Can you make this thing equal as large a negative number as you want? Yeah, so you can make it as big positive and as big negative as you want. So what's the domain? What's the range going to be?
All real numbers.
Yes.
So you make the domain.
Yeah.
infinity close to 0.
Range is going to be all real numbers. You can say ARN, that's fine. Or just say all real numbers. Literally, just write out all real numbers.
R.
We have our nice surfaces. We're going to look at limits. We're going to look at limits. Here's the key difference you have to realize. How many so if you have a surface in front of you, everybody visualize some surface, right? You have some surface, some continuous surface. You have it? Visualize a point on that continuous surface, okay? How many different ways can you approach, if you're walking on your surface, how many different ways are there to approach it?
No end.
There's an infinite number of ways to approach it, right? Before, when we dealt with two-dimensional calculus, when we dealt with a function in Cartesian plane, how many different approaches were there? Two. There was the left hand and there was the right hand. Now, you can approach from any way you want, right? The left or right, the top, forward, the back, or any angle in between, right? You can approach a point from any angle in between. We're particularly interested in approaching down or up the z-axis, down or up the x-axis, and down or up the y-axis. So we really have like 6 common approaches, but really how many are there? Infinite, right? So what's one thing when we've talked about limits? One thing is finding a limit at a certain point, right? Finding a limit at a certain point. What was one way you had to say that a limit didn't exist, to prove that a limit didn't exist at a certain point?
Agree, right hand.
Right and left don't agree, exactly. You find the left-hand limit, and the left-hand limit does not equal the right-hand limit. Or, yeah, other ways too, exactly. Now, in this case, can you possibly test every single possible way? No. So, in general, right now, what do we believe? Is it going to be easier to prove that the limit exists or prove that it doesn't exist?
Doesn't exist because all you have to do is what? Find two different approaches that don't go to the same thing. You fix one of the values, you change one of the others, and if they both go to the same thing, does that necessarily mean the limit exists?
No.
No. It just means that you're definitely not sure if it does or not. Great. But if the two different approaches result in a different output, a different limit, then what can you say? The limit definitely doesn't exist because you have two. Just keep in mind, though, how many possible approaches are there? Many of them. You will have to, in this section, pick approaches. What should you stick to? X, Y, and Z, or maybe something really simple, like y, the path y equals x. Pick really simple paths. You can pick any path you want, so pick ones that are easy to work with. Could you make this as hard as you want? Sure. You could pick some crazy path, like here's the domain, all real numbers, right? You could pick some path that looks like this and just make it crazy. You don't have to do that. You don't have to do that. Also slightly more difficult because we're doing this in 3 dimensions instead of doing it in 2, but it's fundamentally the same thing. Let f be a function in 2 variables, so domain D includes the points arbitrarily close to AB, meaning you have in the domain a neighborhood. Keep in mind a neighborhood in the domain is not just side to side. In this case, it's going to be a circular neighborhood because our domain is what plane? The xy plane. We're taking things from the xy plane. So you have a point AB on the xy plane and you're approaching it. Again, how many different ways can you approach it? Infinitely many, right? So you have this neighborhood around it. Then we say that the limit of f of x as xy approaches AB is L, and we write the limit as xy goes, hey, look, is this pretty much the same notation as you've had before, right here? Yeah, pretty much. Instead of x going to A, you have xy going to AB. If for every epsilon there is a corresponding delta such that blah, 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 blah. That's where most people's brains turn to jelly, right? Let's read this out loud. This says points xy contained in D, so that, what does D represent? The domain. So x and y are the domain, such that, oh, and, what does this represent right here? That's a distance, right? It's a length from what to what? Nope. Distance from, exactly, xy to what? To AB. Then, what does this represent right here? Actually, with the absolute value. That's the what? Distance from what to what? The output of f of xy to what? To L. So remember this, everybody. Epsilon is in the output, delta's from the input, the domain. Delta domain. Just remember that, delta domain. What this means is, for every, you have a point floating out here. You're approaching it in the domain. For every time we get within a certain delta distance, we can get within a certain epsilon distance on the output side. As we approach on the domain, so we could approach really strangely, the output might be up here, but we're getting the range of the potential outputs is getting smaller and smaller and smaller. So let's read that one more time. It says, if for every epsilon,
That's greater than 0.
that's great. Yeah, epsilon's always greater than 0. So what you say is, I want to get within 0.1 of the output value. If this limit exists, if there's a limit there, it means that you can find a delta so that if you're inside the delta, when you evaluate all the points inside the delta, you're going to be epsilon away or less from the output. This guarantees continuity. This guarantees that it's the limit because how small can epsilon be?
0.
No, it can't be 0.
Okay.
How small can epsilon be?
The limit as it approaches 0.
How small can epsilon be?
0.001.
So what does that mean? You can make epsilon
Very small.
as small as you want.
Like
What?
0.
Because it tells you can't. It's not a neighborhood then. Epsilon is the distance away from the output value. If epsilon was 0, it wouldn't be a neighborhood. So what this says is, for every epsilon, if you pick the smallest possible one, what can I always pick? A delta that guarantees if I'm close enough to the input, the output is going to be that close. So no matter how, so what that means is you can get as close as you want on the output, and at the same time I can get as close as what I want on the input. The only way you can violate this is if the point isn't the actual limit. If it spikes up infinitely or spikes down infinitely, or there's some sort of weird discontinuity, where if you get close enough, it just suddenly won't get within that certain distance. Do you kind of get what I'm saying here? It just means that for every epsilon, and epsilon can be as small as you want it to be. We're not going to get into the guts of this, but that's what it means. You need to be able to see it. Well, see it at least. The two paths whose output does not get us in the same place. If that's true, then limit does not exist. I'm also telling you, which is kind of nice. Two different paths, one along the, so let's write this in here. This is along the x-axis, and this is along the y-axis. They go to different values, so therefore, does the limit exist at 0, 0? It does not. Let's see if we can actually see what this looks like and see if we agree with it. Plot it.
Oh, that is cool.
Wicked cool, huh? Oh.
Why is there a gap in the middle?
Well, it's not a gap. What's going on there? It's not a gap. Why does it show that there's a gap right there, or seemingly? What is it?
It like jumps
infinity?
between the 2 points. Oh, is it infinity?
No, it's not because it's infinity.
And
like,
it's
yeah.
like
Is
it
it going
touches
this
each
way?
other.
Yeah, it's like a
What?
line.
Sometimes you see gaps. This is actually really cool. Sometimes you see gaps in your TI calculator graphing. Why do you see gaps sometimes? Or why does it stop? Like sometimes where there's supposed to be asymptotes,
Really steep.
it's too steep. Yeah, what's going on here?
It's going downward.
It's wicked steep. It's wicked, 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 wicked steep. Now here's the thing. Why is the limit not existing here? Well, look what's happening here. Which axis is which here?
It's like a saddle point going to infinity in both ways, right?
Yes. It's a really, really, really steep. Yeah, so this thing goes down. Yay. It's broken there. So the limit does not exist. The limit does not exist. Pretty cool. I think that's pretty neat.
Down really fast to the bottom.
Axis, and we try the y-axis, right? So what did we do there? We did the limit as x0 goes to, hey, 0, 0 is a nice one to go to, of xy over,
Nope.
oh, so what's that going to be? Y is going to be 0, and this is going to be 0, so what's this going to be? 0. And then if we do the same thing, 0y going to 0, 0, this same goes to 0, and what, 0 plus y squared, which is going to be? Does that tell us anything one way or the other? No. That just tells us we found 2 that it goes to the same exact thing. Let's graph this and see what we think. Okay, let's graph this and see what we think. Yeah, I mean, it's just shifted a little bit. Yeah, exactly. I mean, it's also a little different because it's less steep. You're seeing that in there.
Yeah.
Okay, so your homework is 14.2.